Welcome to Module 4, Experiments and Causal Analysis. In this module, we are moving into one of the most important areas of decision analysis, whether one action actually produces a particular result. In organizational settings, leaders have access to large amounts of data. They can see trends, patterns, changes in performance, and shifts in outcomes over time. But the existence of a pattern does not automatically tell us why that pattern occurred. A decision maker may observe that sales increased after marketing, productivity improved after a workflow, or complaints declined after a policy change. Those observations may be useful, but they are not enough by themselves to prove the action caused the result. That is why experiments and causal analysis are so valuable. They help decision makers move beyond observation and toward stronger evidence, instead of asking only, what happened? Causal analysis asks, did this specific action contribute to what happened? That difference is critical. Organizations make decisions under uncertainty, and every major decision involves an assumption about cause and effect. If we reduce price, will demand increase? If we change the website design, will users complete purchases? If we implement training, will performance improve? These are causal questions. Experiments are useful because they give organizations a structured way to test these claims. A well-designed experiment compares what happens when an action is introduced with what happens when that action is not introduced, or when an alternative action is used instead. The purpose is to isolate the effect of the action as much as possible. The organization is trying to determine whether the outcome changed because of the decision being tested rather than because of some unrelated factor. Without that discipline, decision makers can draw the wrong conclusion. Throughout this module, we will focus on the practical logic of experiments. We are not treating experiments as something limited to laboratories or academic research. In business, technology, operations, public administration, education, and many other fields, experimental thinking helps organizations make better decisions. A company may test two versions of a message. A department may pilot a process before expanding it across the organization. A digital platform may test whether a design change improves engagement. In each case, the goal is not simply to collect more data. The goal is to learn whether a decision produced a measurable outcome. This module also requires us to be careful about the difference between correlation and causation. Correlation means that two things appear to move together or appear related in the data. Causation means that one factor is producing, influencing, or contributing to another outcome. That distinction is easy to state, but it is often difficult to apply in real decision-making environments. Organizations sometimes see a relationship in the data and assume that one variable must be causing another. But patterns can emerge for many reasons, including coincidence, seasonal changes, outside events, or other variables that were never measured. We will also examine testing strategies such as A/B testing. A/B testing is a common example of experimental thinking because it allows decision makers to compare options under controlled conditions. Rather than relying on preference or guesswork, an organization can test two versions of an intervention and evaluate which one performs better. This does not mean every A/B test automatically produces perfect knowledge. The test still has to be designed carefully, measured appropriately, and interpreted responsibly. But it shows how experimental methods support evidence-based evaluation and improve decision quality. Finally, we will consider bias in experimental studies. Even when an organization conducts a test, the results can still be distorted. Bias can enter through the design of the experiment, the way participants or cases are selected, the way the intervention is implemented, or the way results are interpreted. If the experiment is poorly designed, the organization may believe it has found evidence when it has actually produced a misleading result. Understanding bias is part of causal analysis. It helps us evaluate whether a result is reliable enough to guide action. By the end of this module, the main idea should be clear. Strong decision analysis requires more than recognizing patterns. It requires disciplined thinking about cause and effect. Experiments give organizations a way to test whether decisions actually work. Causal analysis helps decision makers avoid overinterpreting data, confusing association with impact, and building strategies on weak evidence. Keep returning to one central question. What evidence would we need before we could reasonably say that a specific action caused a specific outcome? That question is at the heart of this module. Now let's focus on how experiments help establish causal relationships in decision analysis. When organizations make decisions, they are usually trying to produce a particular outcome. A manager may want to increase customer satisfaction, reduce processing time, improve performance, raise sales, or decrease errors. The decision itself is an action, but the value of that action depends on whether it actually produces the desired result. This is where experiments become important. An experiment gives the organization a structured way to test whether a particular action leads to a specific outcome, rather than simply assuming that the action worked because the outcome changed afterward. The key idea is control. In ordinary observation, we may see that something happened before something else. For example, an organization may change a process and later notice that productivity increased. That sequence is interesting, but it does not prove causation. Productivity may have increased because of the new process, but it may also have increased because employees had more experience, demand changed, staffing improved, or technology became more stable. Control testing helps address this problem by creating a comparison. The organization examines results under one condition and compares them with results under another condition. This comparison is what allows decision makers to move from vague impressions to measurable evidence. If one group, department, product version, or customer segment receives the change, while another comparable group does not, the organization can evaluate whether the change itself is associated with a measurable difference in outcomes. The goal is not to eliminate every possible uncertainty, because real organizational environments are complex. The goal is to reduce uncertainty enough that the decision maker can make a stronger judgment. Experimental designs are valuable because they force decision makers to think carefully about cause and effect before drawing conclusions. A good experiment begins with a causal question. It asks, in practical terms, if we take this action, what outcome should we expect, and how will we know whether the action produced that outcome? That question matters because organizations often confuse activity with impact. They may launch a new initiative, introduce a new policy, or spend money on a tool. But unless they evaluate the result carefully, they may not know whether it created value. Experiments also support decision analysis by helping organizations move beyond simple observation of relationships. Observational data can tell us that two variables appear connected, but it cannot always tell us whether one variable is causing another. Experiments strengthen the analysis because they allow the organization to introduce a change intentionally and then observe what happens under controlled conditions. This structure separates evidence from casual interpretation. In decision analysis, this is especially important because decisions often have costs, risks, and opportunity costs. If an organization believes that a change caused improvement when it did not, it may continue investing in a weak strategy. If it fails to recognize that a change did produce improvement, it may abandon a useful intervention too early. Experiments help reduce both errors. They give decision makers a clearer basis for choosing whether to continue expand, revise, or reject a course of action. The quality of the conclusion still depends on the quality of the design. The organization must define the outcome clearly, select comparison groups, collect reliable data, and interpret the results carefully. A poorly designed experiment can create the appearance of evidence while still leading to a weak conclusion. For that reason, experimental thinking is not just about running a test. It's about designing a fair comparison. The broader lesson is that experiments make decision analysis more disciplined. They require organizations to ask what is being changed, what outcome is being measured, what comparison is being used, and what evidence would justify the conclusion that one factor caused another. Without experimental logic, leaders may rely on instinct, tradition, or surface-level patterns. With experimental logic, they can evaluate whether a strategy, process, or intervention is actually producing immeasurable results. So, when we say that experiments help establish causal relationships, we mean that they provide a method for connecting action to outcome in a more credible way. They help organizations determine whether a particular decision produced a specific result. They allow controlled testing of changes in strategy, process, or intervention. They help decision makers evaluate whether one factor is truly causing another. They move decision analysis beyond merely noticing relationships and toward understanding whether those relationships reflect real causal impact. Now, let's differentiate between correlation and causation in analytical results. This distinction is one of the most important concepts in decision analysis because it affects how organizations interpret evidence. Correlation means that two things happen together, move together, or show a pattern in the data. That relationship may be meaningful and it may deserve attention, but correlation by itself does not prove that one factor is producing the other. It only tells us that the variables appear connected in some observable way. Causation is stronger. Causation means that one factor is actually producing, influencing, or contributing to another outcome. When we make a causal claim, we are not merely saying that two things are associated. We are saying that a change in one factor helps explain a change in another. That is a much heavier claim. It requires stronger evidence because the organization may use that conclusion to make decisions, allocate resources, change policies, or redesign operations. In organizational settings, data often reveals patterns and relationships. A company may notice that customers who receive more emails also purchase more often. A school may notice that students who attend optional review sessions earn higher grades. A hospital may notice that one workflow is associated with faster patient processing. A retailer may notice that sales are higher in locations with certain staffing patterns. These are all examples of analytical relationships that may look useful. But the key question is whether the observed relationship reflects a true causal mechanism or whether something else is producing the pattern. This is where weak decision making often begins. Decision makers see a pattern and quickly convert it into an explanation. They may say, more emails caused customers to buy, or the review sessions caused higher grades, or the staffing pattern caused better sales. But there may be other explanations. Customers who already intended to buy may be more likely to open emails. Students who attend review sessions may already be more motivated. Faster processing may depend on the type of patient seen that day. Higher sales may reflect location, demand, management quality, or customer traffic rather than staffing alone. The problem is not that correlations are useless. Correlations are often useful starting points. They help decision makers notice where relationships may exist. They can guide investigation, generate hypotheses, and reveal areas where more testing is needed. The problem occurs when correlation is treated as final proof. In that case, an organization may build a decision on an assumption that has not been tested adequately. The result can be wasted resources, ineffective policies, and confidence in a strategy that does not actually work. Understanding the difference between correlation and causation helps decision makers avoid incorrect conclusions and weak decisions. Suppose an organization sees that departments using a new software platform have higher productivity. That may suggest the software is useful, but it does not prove the software caused the improvement. Perhaps only the strongest departments adopted it first. Perhaps managers in those departments were already more organized. Perhaps productivity was improving before the platform was introduced. A careful analyst would ask whether the comparison is fair and whether alternative explanations have been considered. This is why causal reasoning is closely connected to experimental design. Experiments help test whether a relationship is causal by creating controlled comparisons. If two groups are similar and one receives a change while the other does not, the organization has a better basis for evaluating whether the change produced a difference in outcomes. The more carefully the comparison is designed, the more confidence we can have in the causal interpretation. Without that structure, the analyst must be cautious. This also matters because organizational decisions have consequences. If leaders wrongly believe that one factor caused an improvement, they may invest heavily in that factor and ignore the real driver. If they wrongly dismiss a causal relationship, they may fail to scale a useful intervention. Both mistakes are costly. The purpose of distinguishing correlation from causation is not to make analysis complicated for no reason. It is to protect decision quality. So, as we review analytical results, we should always ask what kind of claim is being made. Are we simply observing that two variables appear together? Or are we claiming that one variable directly influences another? If it is the first, we are dealing with correlation. If it is the second, we are making a causal claim, and that claim requires stronger support. Good decision analysis depends on knowing the difference and refusing to treat every pattern as a proof of impact. In this slide, we are looking at how testing strategies, especially A/B testing, support decision evaluation. The basic idea behind A/B testing is controlled comparison. Instead of relying on opinion, habit, preference, or the strongest voice in the room, an organization compares two options and observes which one performs better against a clearly defined outcome. One version is usually treated as the current or baseline condition, and the other version introduces a change. The organization then measures the results and uses that evidence to evaluate whether the change is worth adopting. This matters because many organizational decisions sound reasonable before they are tested. A new product feature may seem more convenient. A revised marketing message may sound more persuasive. A service improvement may appear more efficient. An operational change may look cleaner on paper. But decision evaluation cannot stop at what seems reasonable. The question is whether the change produces a measurable improvement in practice. Testing strategies help answer that question by making the comparison explicit. A/B testing is particularly useful because it reduces guesswork. Suppose an organization wants to know whether one version of a web page leads more users to complete a form than another version. Without a test, the organization might rely on design preference or management intuition. With a test, it can expose comparable users to different versions and compare completion rates. The same logic can apply to marketing messages, customer service scripts, workflow changes, training material, pricing displays, notification wording, or many other decisions. The method helps transform a decision from an assumption into an evidence-based evaluation. The strength of this approach comes from the fact that results are compared across different options. The organization is not merely asking whether performance improved after a change, it is asking whether performance improved more under one option than under another. That distinction is important because outcomes can change for reasons unrelated to the decision. Customer behavior may shift because of timing, seasonality, economic conditions, employee workload, or external events. A controlled comparison helps reduce the risk of attributing those changes to the wrong cause. Testing strategies also support decision evaluation by clarifying what success means. Before a test begins, the organization must decide what outcome it is measuring. Is the goal more clicks, more completed purchases, fewer errors, faster processing, higher satisfaction, or lower costs? If the outcome is vague, the results will be difficult to interpret. A good test forces decision makers to define the metric that matters and then evaluate the decision according to that metric. This makes the decision process more disciplined. However, A/B testing is not valuable simply because two versions are compared. The comparison must be fair. The groups being compared should be similar enough that differences in our results can reasonably be connected to the option being tested. The test should run long enough to gather meaningful data, but not so long that conditions change in a way that distorts the results. The outcome should be measured consistently. The organization should also avoid changing multiple major elements at once, unless it has a clear plan for interpreting the results. Another important point is that testing strategies help organizations learn even when the preferred option does not win. A test that shows no improvement is not a failure if it prevents the organization from investing in a weak decision. In fact, that is one of the most practical benefits of testing. It protects the organization from scaling decisions based only on confidence or enthusiasm. It gives decision makers permission to revise, abandon, or rethink an option before committing larger resources. Controlled testing improves the quality of organizational decisions because it connects choices to evidence. It gives leaders a way to evaluate competing options, measure their effects, and decide which alternative is better supported by the data. This does not mean the test makes the decision automatically. Leaders still need judgment. They must consider cost, feasibility, ethics, customer experience, implementation limits, and long-term consequences. But the evidence from a well-designed test gives that judgment a stronger foundation. So the main lesson from this slide is that A/B testing and related testing strategies help organizations evaluate decisions by comparing results from different options. They support evidence-based evaluation because they reduce reliance on assumptions and create a clearer link between the decision being tested and the outcome being measured. It helps organizations ask not only which option do we like, but which option actually performs better and how do we know? Now, let's evaluate potential sources of bias in our experimental studies. Bias is one of the most important issues in experimental decision making because it can distort results even when an organization believes it has conducted a careful test. An experiment may look organized and data-driven, but if bias enters the process, the conclusions may still be misleading. That is why we cannot treat the existence of a test as automatic proof. We have to ask whether the test was designed, implemented, measured, and interpreted in a way that supports a reliable conclusion. Bias can begin with the design of the experiment. If the experiment is not structured around a fair comparison, the results may favor one outcome before the test even begins. For example, if one group receives a new process while another group continues with an older process, the comparison only helps if the groups are reasonably similar. If the new process is given to the most experienced employees, strongest customers, or best performing locations. Better results may reflect those pre-existing advantages rather than the process itself. The experiment may appear to show impact, but the evidence is weakened because the comparison was not fair. Sampling is another major source of bias. The people, cases, departments, transactions, or observations included in a study must represent the decision context the organization actually cares about. If the sample is too narrow, too convenient, or too different from the larger population, the findings may not generalize. An organization might test a service improvement with highly engaged customers and then assume the same result will appear among all customers. It might test a training program in one office and assume every office will respond the same way. Sampling bias makes the results look stronger than they really are because the experiment is based on a group that does not reflect the broader setting. Implementation bias can also distort results. Even if the design looks good on paper, the way the experiment is carried out matters. If one group receives more attention, clearer instructions, better support, or more motivated supervisors, the outcome may be influenced by those differences rather than by the intervention itself. This is especially important in organizational settings because people know when they are part of a change. Managers may push harder, employees may behave differently, and participants may respond to attention rather than to the actual change being tested. The experiment may then measure the conditions surrounding the test instead of the effect of the decision. Measurement bias is closely related. If the outcome is measured inconsistently, vaguely, or selectively, the results can become unreliable. Suppose an organization wants to measure customer satisfaction, but one group is surveyed immediately after service, while another group is surveyed days later. Suppose productivity is measured differently across departments. Suppose errors are counted more strictly in one condition than another. These differences can create artificial effects or hide real ones. A strong experiment requires clear, consistent measurement because the conclusion is only as reliable as the data used to support it. Interpretation bias is another serious concern. After results are collected, decision makers may interpret them in a way that confirms what they already wanted to believe. They may focus on favorable metrics, ignore inconvenient findings, or treat a small difference as meaningful without enough evidence. This is common because organizations often have emotional, political, or financial investment in a decision. Interpretation bias weakens experimental conclusions because the evidence is filtered through expectations rather than evaluated objectively. Bias weakens confidence in experimental conclusions because it introduces alternative explanations. When bias is present, we can no longer be sure whether the observed result came from the action being tested or from flaws in the study. Decision analysis is supposed to improve the quality of decisions, but biased experiments can give decision makers false confidence. They may believe they are acting on evidence when they are actually acting on distorted evidence. Recognizing bias helps organizations evaluate the reliability of experimental studies. Real-world experiments almost always involve limitations. The goal is to understand those limitations clearly. A responsible decision maker asks whether the design was fair, whether the sample was appropriate, whether the implementation was consistent, whether the measures were reliable, and whether the interpretation was balanced. So the main point is that bias can enter at several stages: design, sampling, implementation, measurement, and interpretation. Each source of bias can distort results and weaken the connection between the experiment and the conclusion.